Hello again, folks. So this last video for this chapter is all about exceptions, looking at structures that are not quite the standard. How do we deal with structures that don't always follow the rules, and how we're going to be treating those? So let's go ahead and get started so we can finish up. Okay, exceptions to the octet rule. That not all atoms will obey the octet rule all the time. There are two major exception classes, one of which we've already seen previously, and that falls into incomplete octets, which under the less than 8, and expanded octets, or expanded valence shells. Now, the incomplete octets are the simplest enough that they will not have enough electrons to give the center atom an octet. That's usually the situation. Anytime you have atoms from group 1, 2, or 3, you're not going to be able to achieve an octet because you don't have enough electrons. The big major organic version, or non-metal version, is boron. Boron has 3 electrons, so it cannot achieve 8 without getting a formal charge. So it is impossible for boron to normally achieve an octet. However, boron and the like are not the only examples. Nitrogen is the only atom, really, it's one of the few atoms that has nitrogen often will give us an odd number of electrons. If when you count up your electron count, you get an odd number of electrons, it's going to fall into this incomplete octet situation. An odd number of electrons creates something called as a radical. Basically, an unpaired electron. Instead of a lone pair, which is the 2 dots, you have a single electron by itself. This is often highly reactive. So, if you can form a radical, these guys react very quickly. Many of our gases that are exhaust gases, the nitrogen monoxides, dioxides, trioxides, often will have radicals associated with them, and that's why they are so reactive in the upper atmosphere. So a radical is essentially an incomplete octet, and it should be 1 less, and if you can put it somewhere, it's often on the less electronegative atom, if at all possible. Now, expanded octets are just the opposite. It's sometimes atoms are going to try to make more bonds than they should have any right to make. This will only occur in elements beyond row 2. So rows 3 through 7 are capable of achieving a expanded octet. So that means not carbon, not nitrogen, not oxygen, not fluorine, but any of the other atoms can achieve an expanded octet. Why? Because 1, they are bigger, and 2, remember, rows 3 and beyond have access to that empty d orbital. Because they have access to that empty d orbital that's not being used, they can put any excess electrons into that d orbital and thus stabilize it. But expanded octets can be used to reduce the formal charges, and expanded octets structures are typically the the most stable version of the oxyanions you can draw. But expanded octets can never occur in group 2 elements. Now, keep that in mind. That's why carbonate doesn't have 4 oxygens, because if it had 4 oxygens, it would have an expanded octet. Phosphate can have 4 oxygens. Perchlorate can have 4 oxygens because it's having an expanded octet. So don't worry. If the central atom has more than 8 electrons, that is okay, as long as it's not row 2 element. So with that in mind, let's revisit our Lewis rules. We still want to sum all valence electrons up. Now we also want to account for the overall charge. We will select the central atom as the least electronegative atom, one that can make the most number of bonds. Still, we can use the formula to help. Connect all other atoms to the central atoms by single bonds. Still want to distribute electrons to the outer atoms to give them octets or duets. Still want to assign any remaining electrons to the central atom. We still want to move lone pairs into multiple bonds to give the central atom at least an octet. But now on step 7, we want to account for all these weird exceptions. Poke around at the exterior. We still want to make sure all electrons are accounted for. We still want to make sure the outer atoms achieve an octet or duet. And the inner atoms try to achieve an octet if possible, especially in case of row 2. We want to keep all formal charges low and assign the atoms charges to the atoms with the appropriate electronegativity. So we have a few more practice problems. I'm gonna write these down real quick and we'll go through these guys. ClO4 1-, xenon, tetrachloride, and BF3. So let's look at the doc cam. Okay. So, So with this in mind, chlorine has 7. Oxygen has 6. There's 4 of them. That's 24. And we have 1. So 24 plus 1 makes 25, plus 7 makes 32. We're going to put chlorine in the center. Chlorine is less electronegative than oxygen. It also comes first. So that's also another dead giveaway. Put oxygen, 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 oxygen. Okay. Now, 2, 4, 6, 8. We're down to 16 again. Not 16, 24. 6 on each outer atom. That uses up all 24. Everyone has an octet. So technically this is a stable structure. It's a valid Lewis structure. But let's look at the possibilities. 1, 2, 3, 4. The formal charges. I know. Oh, God. Why? 3, 0, 4. Right now, and chlorine. Chlorine should have 7. Each oxygen should have 6. Count them up. They're all the same. 1, 2, 3, 4, 5, 6, 7. And chlorine 1, 2, 3, 4. Plus 3 and all minus 1s. So this structure has a huge amount of formal charges. is there a better structure that we can draw? Well, let's see what happens when I take one set of lone pairs off this and make it into a double bond. Sure, oxygen, sure, chlorine starts to adopt a higher expanded octet. Now this oxygen is, now this chlorine is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 on the chlorine, but what happens to everything else? So 6, still minus 7, 6, minus 6, 6, minus 7, 6, minus 7, and 7, then 1, 2, 3, 4, 5. Every time I do that, plus 2, minus 1, 0, minus 1, minus 1. Each time I expand this octet by 1, well, by one set, we lose one matching pair of formal charges. So we want to get the formal charge of chlorine down to 0. So that means I can do this 2 more times. And so I'm going to skip straight to the second time. So chlorine, double bond, double bond. It doesn't really matter which one you you put as a single bond, because of resonance allows us to move this around. We have a single charge, and I can draw 4 resonant structures from this, including this guy. 1, we can put charge here, put the charge here, put the charge here. So the oxygens are only feeling the charge 1/4 of the time. So it's okay that it has an expanded octet. Boom. That stabilizes this. What about this? Xenon. Oh my God, xenon. Oh. Well, xenon is a noble gas, so that is group 8. 7 times 4 is 28. 28 plus 8 is 36. Put xenon in the center. Chlorine, 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 chlorine. We used up 8. 28. I'm going to put 6 on each chlorine. That's 24. So we have 4 more electrons left. Where do they have to go? The number 1 rule is you slap the remaining electrons left on the center. Yes, I know that makes xenon have 2, 4, 6, 8, 10, 12. This guy has 12 electrons instead of 8. But all the chlorines have 8. 2, 4, 6, 8. They all have a formal charge of 0. Everything has a formal charge of 0. 1, 2, 3, 4, 5, 6, 7, 8. So this is stable despite its expanded octet. So sometimes that is the best you can do. Boron 3, and then 7 times 3 is 21. So 24. That makes up 6. So we're down to 18. You could leave this like here, or you could try to draw a resonance structure. Right now, each of these atoms have 8 except for boron with 6. But there's 0 formal charge. If I took away one of these lone pairs, I could draw a structure that looks like this. However, this is very, very unstable, as you will see in a second, because this would put a negative on the very positive boron and a positive on the very negative fluorine. So it really goes against the normal scheme of things. And so that's not super stable. I'm going to make up two other ones wholesale. Let's put PF5. So 5 and then 7 times 5 is 35, so 40 electrons. P in the center. F, 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 F. 2, 4, 6, 8, 10. We used up 10. 30 left. 6 per fluorine. That's 6, 12, 18, 24, 30. I have no more electrons left. All the outer atoms have 8. Phosphorus has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. Perfectly okay. How many? What's the formal charge? 5 minus 5? 0. 0 formal charge. This is stable. Don't need to do anything with it. It's stable. And last one, last but not least, I'm going to make NO2 neutral. So 5, 6, and 6, 12, so 17 electrons. Ain't no way to make this neutral. Ain't no way to give everyone an octet. We have an odd number of electrons. So, O, that's used up. That uses up, 4? So we're down to 13. Use up 12 right here. Slap 1 electron on here. Now, 1, 2, 3, 4, 5. We're going to take 1 pair and put out, now this is 7, 8, and 8. Technically, it's a formal charge of 1, formal charge of +1. Is that valid? Absolutely. You can't make it any better than this. This guy has 7, everyone else has 8. We do have a resonance structure that shifts that charge around. But that's as good as we're going to get with that guy. So, okay, the last 2 slides of this chapter, it involves electronegativity and bond polarity. Why is it important to consider electronegativity and bond polarity? It's because, well, what happens when we have electronegativity differences? Well, the uneven electron sharing leads to what's called a polar covalent bond, or a polar bond. A polar bond is a bond where the atom of the higher electronegativity attracts the bonding electrons more strongly, so it achieves a partial charge. We use the Greek small letter d, the delta symbol, to represent the partial. So partial negative charge, delta minus, or the other atom adopts a partial positive. And when we achieve a partial negative and a partial positive within the same atom, we achieve what's called a dipole. And this gives the atom a ionic-like character, meaning it's going to react similar to ionic atoms in that they'll be attracted to other charged atoms. The more polarity you have, the more polar bonds, the more ionic character, the stronger it is. We can actually measure this by finding the difference in the electronegativity. Generally, the larger electronegativity difference, the greater the polarity, the greater the ionic character. And we can actually rank bonds on a continuum from nonpolar, where the difference is 0, to ionic, where the electronegativity is really very high. However, there's no really good set cutoff. I will give you one for polar versus nonpolar, but what separates polar and nonpolar is up for debate. What separates polar from ionic is up for debate, because simply you're just subtracting out the differences in electronegativity. However, while we will not actually do this, it is possible to calculate this as a force called a dipole moment, given as mu. This mu is the measurable magnitude of the charge separation caused by the dipole. And the mu is simply the charge, Q, times the radius of the bond length. And this is measured in debye, where a debye is equal to a coulomb, this coulomb meters. Now, we won't actually measure this. It's just good to know that there is a way to quantify this, just not that we're not going to worry about it. But it's possible to calculate the ionic character by comparing the measured dipole moment to what would be possible if the electrons were fully separated, like in an ionic bond. So if you compare those, you can compare the ionic character, like 10%. It's only 10% of what it would be separated in. We're not going to bother to do those calculations, and so don't worry about it. Just know there is ways to calculate these things. With that in mind, that is the end of this chapter. I hope this has been useful. Have a good day.